So what is an interpreter? It's a thing that runs a program, essentially. So you start with some program text, it's a string, and then you turn that into a magical tree. You're going to skip that entire first part, so forget you ever saw anything. We're starting here. We have a tree that sort of represents a bit of computation. Like maybe you multiply things, maybe you add things. And then the interpreter takes that and turns it into an answer. So that, for our purposes, that is what an interpreter does. It takes a computation tree and turns it into an answer. So,
Is that like any computation or just strictly like?
it's a very vague definition.
Okay.
Whatever the language is.
Yep. What is a language? A thing that is interpreted. So, okay. So let's actually start with our definition of. Hold on. Should we have just before? Also, I am not good at using Xcode. How's the legibility of
We've
that?
done a presentation large.
Okay. Good in the back?
You can switch to Emacs or whatever it is you use.
No, we're doing playgrounds.
Eclipse.
So we're going to be calling our trees expressions. That's traditional terminology. And ignore this word for now. Okay, and so what the simplest thing is an expression can be a number. And that's just throw a double in there or something. And as we're also going to say, an expression can also be adding two numbers together. But we don't want to say two doubles because we want to be able to chain these together. So you can add two expressions. So you get an entire tree like this one where, well, we don't have A, B, and C yet. We'll get there. But we have 7 and we have plus, and now we can also define times. And so this is just, we have now written our first language. And now let us write a program in that language. And it will just be an expression. Let's add 2. So another expression. So number 2 to number 2.
It's really the ugly version of list.
Yes, all versions of Lisp are ugly.
We're cheating a little bit because we were using double. If we didn't have double, we would have to define number system.
I mean,
that kind of stuff.
The thing about interpreters is you're always writing them in a language, interpreting another language.
Yeah.
And so we're going to be using a lot from the host language, and that's part of what makes interpreters really fun and easy to write. Like, we can't just reuse these doubles. We don't have to define binary arithmetic if we don't want to. So, now let's run this, and we will see. Look, our example 0 is a plus with 2 numbers. We didn't actually add anything together because we haven't yet told it how to add anything together. So, now we will say, now we will write the interpreter. And it's called evaluate, also because that is traditional. And what it'll do is it'll take an expression and it'll give us back a double, because that is sort of when you add various things together, you'll get back a number. Okay, so now how do we actually write our first interpreter? We only have one thing available to us, and that's this expression, and it's an enum, and the best thing to do to enums is switch on them. So we'll go ahead and put that down. Okay, so if we have a number in, then what should our result of evaluating this number be?
The number.
Exactly. We return in. Okay, that was the easy one. The other two aren't bad. So now what if we have a plus sign? Well, we'll just return left plus right, right? Because we're supposed to be adding these together.
Since we're yelling things out, I'm just going to praise the fact that you put let left, let right instead of case
I've
left?
been going back and forward all the time.
Case left, Tyler.
You did it
Why would you
correctly.
praise her for that?
Case left, Tyler.
All right.
That's wrong.
And so immediately we run into an error. And that's, we can't add expressions together because if we look at our definition of plus, it is two expressions. Well, so what can we do with these expressions then?
Evaluate them.
We can
We
evaluate.
can evaluate them. We have a thing that turns expressions into doubles, and we are halfway through writing it, but that doesn't mean we can't use it. So we recursively call evaluate, and that'll turn that left-hand side into a double, and then we can evaluate the right-hand side and turn that into a double. And then we are going to copy and paste and do the same for times, except we're going to multiply instead of divide, or add, whatever. Okay, so the errors have gone away, and we have defined an interpreter. Let's see if it works. And we get 4. Amazing, we have added 2 and 2 together. So, like I said, interpreters are actually not that hard to write. And the rest of this will be me just adding more and more complicated features to the language and extending the interpreter to continue keeping up with these features. So, the next feature I'd like to add is a variable. So what is a variable in the data structure of a language?
It's just a name.
It's just a name. So, we give it a string. Okay? And now let's update our expression a little. Let me find the white space because we have to do that. Okay, now instead of saying 2 plus 2, we're going to an actual useful function. Not really. And we're going to say, what is 2 times 2? And then we're going to take all of that, and we're going to multiply it again by pi and compute the area of a circle. Okay, so that's, we now multiply this by a variable. And like I said, how we were skipping parsers, that makes this whole writing these programs really ugly, but it's easy to do, and it works well enough. And parsers are very fun, but they're a separate topic. So we use the variable. Okay, great. So we now have updated our example program, and we expect to be able to find the area of a radius 2 circle. So now our switch statement, since we've extended the enum, our switch statements no longer a thing. And now we have a variable name. But there's not really much we can do with a variable name because we sort of don't know what any of the variables should do. So we're actually going to change the definition of our evaluate function to take a parameter which for now I am calling what the variables mean. And it is a mapping of strings to doubles. And we are actually going to extract that and put it in a type alias and call that an environment, which is just a very generic word, but it is what the variables mean. Okay, so now that we know what the variables mean, if we have a variable, we can just return, what the variables mean, and just look up the variable name in that.
What if it's not there?
It's an interesting question. Let's fix some more syntax errors and get back to that.
Stick an exclamation mark.
Yeah,
What could go wrong?
that's one solution. We are using the language we're writing in to define the features of the language we're interpreting in. And our language we're writing in, Swift, has this wonderful feature called crash if something bad happens. And we can actually just inherit that into our interpreted language, and it will crash if something bad happens too. But since this is a recursive call, we're going to just pass through this new value, because what the variables mean doesn't change inside of a plus sign, the variables still mean the same thing, so we just pass it through unchanged. Okay, so now let's go ahead and do that. Just, so we fixed, but now we need to update this. So we need to pass it a list of all the variables we're using, and our program crashed, as predicted. So if we actually tell it that pi equals 7, then we now suddenly get a result. So let's go ahead and extract this out and maybe correct any math errors. And so along with this environment, we're going to say, let the default environment, and this is just for convenience, it's an environment, and it is pi is double.pi. Okay. And now we can just pass in the default there. Great, and we get, that's probably the right result, I don't know. Okay. So now we have variables, but they're not really very useful because you kind of have to set all the variables at the beginning of a program. So let's add a new language feature, and let's add let bindings, which are very similar to lets in Swift, but without the complication of having to worry about scope as much. We're calling them let binding because using reserved words is asking for trouble.
Backticks.
It's just the confusing code. Okay, and what that is we say, okay, I have a string. I want to take the result of this expression and put it in the variable that is represented by that string. But it only does that inside the scope of a this is still well scoped, still following lexical scope. And it only does it inside of this other expression, this inner expression. Now we don't have to worry about like finding all the variables in a function because we just syntactically say this variable only applies in this setting. Just adding a few more labels to hopefully make it a little better.
So not writing back up.
No,
It's more like Haskell.
not even writing Swift, because like in Swift you can just say let A, let B,
Sharp
let
or
C.
Haskell.
But this is simpler because simpler is easier to write an interpreter for. Okay. So let's keep going with this example. But now we'll say we want expression.let binding. And we want the string to be radius, because we want a variable called radius. And we're going to say the radius equals the number 10. And so now we're saying, okay, so now inside this expression, radius will mean something, and then we can put back this thing we had. But instead of 2, let's just say variable radius. So this is, we want to square the radius. And then multiply that by pi. Check our close parentheses. Pretty sure this indentation is wrong, I'm sorry. Okay, so once again we come up to an error that we don't have all our switch statements done. So once again we have a variable name. We have an equal expression, and it is a body of code that we evaluate with that new variable like this. So the first thing we need to do, actually, does anyone know what the first thing we need to do to evaluate this is?
So you probably have to evaluate the equal expression so you know what to associate with the variable name.
Yep. So let's say the binding value, I don't love that name, but, and we evaluate the equal expression, and that is in what the variable means as the environment. Now I am going to change this because I like this name, but it's too long, and it's also non-standard.
No, go back, undo. Double click what the variables mean up in anywhere, and then Control Command E.
Nope, that's my shortcut to open Emacs.
Okay, right.
Edit all in scope.
Yeah, it's in the editor.
Or you push the little button on your.
Edit all in scope, one down.
Oh, there we go.
Boom.
Excellent. When technology works, it's amazing.
Type the new name. There you go.
Okay.
Boom.
Refactoring never works for me, and I still try to use it.
But that's different.
That's not
That's not the
What even
refactor.
that?
It doesn't.
That's a kind of refactor. Okay, so, all right, we're still not done. So we have the new value, and now we need to evaluate the body of this expression, right? Let me try to keep some consistency there. But we needed to know about the new value. So we're actually going to now make a new environment, and it's going to be a copy of our old environment, but we're going to update it with, well, hey, now we know a new variable. This variable name that we're binding is going to equal our binding variables.
So I think you want a new environment instead of ENV on line 37.
Yes, and that is an error. Because environment is not mutable, which is good, because we actually don't want this binding to escape. We don't want to be setting global variables. All right, so now we just return evaluate body expression with our brand new environment. Okay. Type errors have gone away, and we get 314, which is the correct result for a radius 10 circle. So, just to experiment, let's say we try and add the result of this to radius, which is outside of where radius should live, because it should only, variable radius. Okay, so that type checks, and it crashes, because we tried to use radius outside where it was defined. It only, this environment only survives the duration of the value of the body. Great. Undo all of that. And let's actually fix the crashing problem, because we can handle errors. So what kind of interpreter errors do we have? So far, we only have variable not found. And it just is a string and a variable. It inherits from error. Okay, so let's make our evaluator throw, because we're good citizens, and it sometimes does go wrong, so we should say when it goes wrong. Throw in a bunch of try statements. Now, we should fix this exclamation mark that we put in. Just make sure that we actually get a value. Otherwise, throw interpreter error, variable not found, variable name. Okay. So now we have a function that throws when it has an error and doesn't just crash. More or less. Okay.
I'm missing some tries on the times and the half for the right side evaluation.
30,
That should be good.
on the right
On
hand
the
side.
right hand side.
Try has lower precedence. try should cover the whole statement. Yeah, Swift actually doesn't, is very picky where you put your tries.
The fact that you know the precedence of try tells me that you've done
I did too far. Okay. We may have to, no, I think we're good.
You
Okay.
undid the,
I did undo the breaking change,
breaking.
so. So if we spell this radius wrong, then we should get back our error. And actually, we still are crashing, but because we're throwing in the top level, but it's better. It's
Yeah.
cleaner this way.
At least you get
And it
nervous.
couldn't find the variable radius. Okay. So that's basic variables sorted. Next, I would like to add lambda and closures, because that's the next easiest thing to add, surprisingly.
As long as your language doesn't separate the concept of lambda and function.
We don't have functions, we just have. Okay. So we're going to, and there, I will make a note of terminology here. Swift calls both lambda and closures, but traditionally there's a difference between the two, and I'll explain that as we define. But a lambda is saying, I take in a variable as input, or not one. I take in a whole list of variables as input, and then there's a body, which is an expression. And that's, since we don't have types, that's all that lambda is, that's all that a little anonymous function is. If you've ever written, we'll soon be able to write this in our little example language. Except this needs types, like I was saying. Okay, but just actually defining lambda is completely useless, because it's also, you also need to be able to use the lambda. So we're also going to add a function call to our language, which takes in a function expression, which is an expression, and some, actually I should name this too. These are the parameters of the lambda. And these take in arguments, which is a list of expressions again. So now our language is actually something interesting.
I don't know, it was pretty interesting before.
Yeah, this is how easy it is to implement a calculator. Like we just implemented a calculator in 20 minutes or whatever. It's, especially when you don't have to deal with parsing, when you leave that to someone else, it's fun and easy and everyone should do it all the time. So, all right. So there's one change we should make now. We've been using doubles everywhere, and now that we've added lambda to our language, we're not all values are doubles anymore. Some values are closures, which is not lambda. So we're going to create a new data type called value. And the value is either a number, which is just a double as before, or it's a closure. And a closure, let me put this in a comment because Swift doesn't like when you write what I want to. A closure is exactly a lambda plus an environment. That is, it is a lambda that has closed over its environment, and that is where the name closure comes from. So, we're going to just copy and paste the inner workings of lambda, because annoying reasons. And then we're also going to add an environment. And that's just an environment.
You change your order of the type alias for plugin.
It should be okay.
Did I fix that?
Yeah, it's fine.
They're going to be mutually recursive, so. Now, what is our environment? Is our environment just mapping variables to doubles? No, we also need to be able to map variables to these closures, so it's now string to values. And now we wrap this in between them. Okay. So that's good for now. And now, once again, we're back to the familiar error. We added new values to our enum. We need to add new cases to our switch statement. Actually, let's fix the errors first. First of all, our evaluate doesn't return a double anymore. It returns a value, which is where the name evaluate comes from. It turns expressions into values. Okay. So now our plus, our number's broken. A number should return a number. I'm going to make this explicit, even though Swift doesn't. Swift is able to infer, but just an expression number gets turned into a value number. So, now what do we do in the case of plus? Swift is saying it doesn't know what to do if someone tries to add a function to 4. And Swift is right, we don't know how to add a function to 4. So we should make that explicit.
Don't you have to evaluate the left, see if it's a value, a number?
Yep. Actually, let's do that in multiple lines because I'm not keyboard golfing. I have to tell myself that. So the left value is just equal to the evaluate. The right value, I'm a big proponent of copy-paste coding, is just evaluate the value. Try to evaluate. Okay, so now we're in trouble if either of these things is not a number, because numbers are the only things we know how to ask. So, guard case.
Guard
Dot.
case,
Case let.
Okay,
Guard
guard goes
case.
inside. Dot number, let left number
Oh, yeah, okay.
equals left value.
Well, but no, you can do it, you can do case let too.
You could, yes.
If
I'm trying to stay consistent.
If you're,
Briefly.
if your syntax requires a gosh darn such and such syntax webpage,
Okay, so we make sure both of the things are numbers.
great web guard case.
If they're not,
I can't remember.
else.
I've got it down.
Okay. Then we need to throw a interpreter error dot primitive
Check this
or
page.
bad primitive. Oh yeah, type error. Yeah, we'll just call this a type error. And we won't be more detailed. If you're writing a real interpreter, please be more detailed. So we add type errors to our list of things that can go wrong. Remember the capitalization convention for the language we're working in. Okay, and now we can return left value plus right number. Thank you. Okay.
And it needs to be boxed.
Yes, and since we need to tell it that this is the number half of the value, remember our values can be either numbers or closures now. When I'm pointing on my screen, you can't see that. That it's a number. And we're actually just going to, in a real interpreter, you should probably not just have cases for every single primitive number operation you're doing, but we're saving time by copying and pasting. Okay. So that's those errors fixed, and now we're back to the problem of our switch statements missing cases. So, how do we evaluate a lambda where we have parameters and a body? What value should we return here?
A new environment. Closure of the environment?
Yes. So, if we look at what possible values we have, a closure is a lambda plus an environment. And inside evaluate, we have an environment. And inside this case, we have a lambda. So all we do is we just say, this lambda is going to close over its environment, and that is how a lambda turns into a closure. So, parameters, just copy those. And you don't actually evaluate anything when you run into a function definition. You just make a note of everything that you need to calculate that function, when you finally get that the last parameters. Okay. So, now the really fun case is function. So we have a function expression. And a argument expressions. Because we're allowing multiple. So the first thing we do, much like addition, much like specify, the first thing we do is we take this expression and we turn it into something we can use. So function value is going to be just evaluate whatever in the function expression in the current environment. Try to do that. And our argument values, they're just going to pretty much be the exact same thing. We're going to take our argument expressions and then just map, and for every single one of them, we're going to say, evaluate that in the environment. And so far, so good. Okay, so now that we've done the easy part, the question is, how do we actually make the function call? Well, the first thing we should do is do some sanity checks. Because what if this is the number 3? We're in trouble. So, we're going to guard case that it better be a closure. Fill that in later. And we'll fill that in later too. Okay. So, and the closure has parameters, it has a body, and it has a closure environment. And if not, we throw a type error.
Each one needs
Alright,
a
I
type.
need more lets. Yes.
I can just do one.
But then you'd be wrong.
Well, but then you couldn't change this one to a bar. Okay. So, the next thing we do is this closure environment doesn't actually give you enough information to evaluate the body yet. Because if we had A, B in A plus B, just knowing all the stuff outside doesn't tell us how to evaluate A plus B. We need more things in our environment. We need to put A and B in our environment. So, we actually need to put one more thing in our guard statement. And that is we have 2 arrays. We have argument values and we have parameters. And they better be the same length. Because if you try and apply 2 arguments to a 3-argument function, that's an error. Or in JavaScript, that's an implicit undefined, and it just works.
And that's a bad one.
Okay. So now we know we have a function, we have all our arguments, they're the same length, we're ready to go ahead and modify our environment. So, for every parameter and argument, and I am using 2 words for what's kind of the same thing. The parameter is like the string x, and the argument is x means 4.0. But we have both, and we need to pair them together. So we just zip them together, which is fine because they're the same length. Call that argument value. And then we'll just go ahead and update our environment and say that parameter now means the argument value. That's a value, so we can do that. And we have a perfectly good environment, and now we can finally just evaluate the body in the new environment. Okay? get type checked. And we haven't written a good example yet. But, spoiler, we've just written a Turing complete language. So let's, it's environments containing values containing environments containing values, which is as good as an infinite tape. So, let's modify this to actually use a lambda, which I probably should have done at the start.
Can we get another example? Or do you wanna just take that one?
You can make it.
Don't know whatever's easier.
I did call it 0, like expecting that I would actually create more than one. Okay, so now we're going to we're going to instead say, we're going to define the variable calculate area. And instead of a number, it's going to equal a lambda. It'll actually only take one parameter, which is radius. And then the body. And this is a terrible way to write programs. I think I've already mentioned that. And then in the body, we do 2 multiplications. We multiply radius times itself and then multiply it by, which is a constant that we've defined. Close all our parentheses. Okay. Right, but this is a let binding. So, now we actually get to use our lambda function call. Dot variables. And for the arguments, we say number 20. This is not the most exciting use of a closure ever, but it should tell us that things are working as expected. The first time I tried to do this, I was using the wrong environment.
Change your exam.
Yep. Okay, we get a new number. That's probably right too.
That looks about like 400 times 3.
Yeah, pretty close. Okay, so Turing complete language, done. You do not want to try writing any real programs in this language for several reasons. It's still very primitive.
I think I'll do advent of code this year.
You technically could.
I know.
It would not be fun.
You should get bonus points.
Okay, so where shall we go from here? There are actually lots of different options. This is sort of a little tiny version of what people like to call the lambda calculus, which is a fancy way of saying it has functions, and you can call them. And you can add mutable variables to this. You can add recursive functions to this. You can add tuples, simple enums.
It would be interesting to see calculation of a Fibonacci sequence
Fibonacci.
using a recursive function. I don't want to. If anybody else has a more interesting thing, feel free.
Well, that sounds very interesting.
Okay.
I do want to make sure we have time to do it.
Yeah, and we are currently,
If you can do it in
We don't-
4 minutes.
we don't have a lot of time, we have a little time.
You can do it in 4 minutes.
We can do it in 4 minutes. It may be a little rushed on the explanation. So for no reason at all, we're going to create a new class called Box. And Box is the most boring class you have ever seen. It holds a value and nothing else. So a box of T is just a T. And you can create one with any value you want to put in it, and you can get that value back out of it. Okay, that's super boring. The only reason we did this is because now this is a mutable box. We are borrowing mutable state from Swift and using it not quite to do mutable state, but a little bit of mutable state in that language. Now we're going to update our value, take a key out of JavaScript, and create a new undefined value. We could also use number 7, doesn't really matter. Okay, now we're going to make a change to our environment. Our environments no longer stay the same forever, because now they hold boxes of values instead of values. And that's a very similar thing to holding a value, except that you can change your mind about what's in that box at any time, which we will use for one thing only. And now we have to say, this is a box that holds pi, not pi itself.
A pie box.
So right now, this is just a, so we peer open inside the box in our variable case. We create a new box in our let case. And we have just done absolutely nothing. If we run this, we get the exact same result because we really changed nothing. So now we're going to make a very important change to the let case. This is going to stay the exact same, except I'm just going to call it something different. It is now a let recursive instead of a let binding. Okay, we didn't have to make this change, so it doesn't care what you call things. Okay, so but we're going to change how we reason about it. And that is, we're going to create the environment first, and then evaluate this binding value. So we're going to move this line up, and we're going to say the new environment and variable name is just, it's a box, and it holds value.undefined. Okay, that's pretty boring. Actually, we're going to save it to its own variable, so we can keep track of it and update it. And then we put this in the environment, we put undefined into the environment. And now, instead of saying we evaluate it with the old environment, we evaluate the thing we're binding recursively with the environment containing it. And this is how you get recursive definitions. And then instead of putting this directly back in, you just say the box.value, now that we've finished, is we have used mutable setting to tie the recursive knot, as it's called. Okay, I think we just implemented recursion. I have no confidence. Let's.
Need to define Fibonacci.
Actually, we need two more cheating things before we can do Fibonacci. Let's see.
Factoid.
Sorry, or either Fibonacci or factorial.
Yeah, and this statement.
Yes, we need an if statement. But we're going to use a highly specialized if statement to save time and optimize our programs for writing Fibonacci. We're not going to add booleans to our language, we're just going to add if 0. So this is the test expression. And if that is true, then we want to evaluate the then expression. And if it is not true, then we want to evaluate the else expression. And I think that's all we need to add. Okay. Now we go back to our error, and it says you added a new thing, you need a new case. Test expression. Expression. Okay. So we have our expressions. We want to only evaluate the test expression because that's the magic of if statements, is that they don't evaluate everything. They only evaluate some things. So that test value equal evaluate test expression using our environment. That's pretty standard. And so now, how do we do an if statement in this language? We borrow the host language's if statement. So we say, Swift says, if this is the number 0, then return the evaluation of the then expression. Else, copy, paste, change. So we have just borrowed Swift's if, and now we have if in our language.
Need some tries. You need a colon at the end of the case.
Okay, is it like that?
And another try.
One more try. Okay, so now we should have everything we need to implement Fibonacci or factorial. So, now this is going to be a little ugly, I'm going to warn you. So the first thing we do is we say let expression, let recursive, Fibonacci, or fib, and that's going to equal, going to need space for this, a lambda that takes in one parameter, let's just call it n. Figuring out how to do white space is the hardest part about this. And what do? What the body is, if n is 0, if the variable n is 0, then we return the number, okay, what, yes. Okay, what if it's not 0? Then we are going to add together a function call.
To fit.
What did I call that? Call function? Function call?
What was call function?
Okay. The autocomplete is not happy.
Isn't it plus?
Yeah, it's
Oh,
that's
okay.
right, yeah.
That's call function.
Nah, I think it was functional. Yeah, there you go.
Okay, okay. And wait, the variable fib, because it's stored in a variable, we have to. And I'm just gonna say, if you wanna make this a little nicer, you can overload like integer convertible and get rid of some of these things. And you can make typing the language in directly a little nicer, but so for clarity, I'm not, because this code is clear. There's no magic. An interpreter is just a program. That's sort of what I want to get across. Okay, so now we need the arguments that we're calling fib. We have plus, variable in. We're adding -1, because we didn't do subtraction. That's fine. Don't need it. And to that, we call something very similar, except we subtract 2. Okay, I think that's the definition of Fibonacci. So now we actually need to, so we've defined this in our let recursive. We've defined fib equal to this big ugly lambda thing. And so now we can call it, we can set a function call, fib, and give it some arguments.
So you're gonna have negative numbers?
That's a great question. Do we? Let's look at our values. A number contains any double.
Well, I know, I'm saying
for if 0.
for if 0.
Oh,
I
okay.
think actually if.
You're right. I did this. This isn't if 0. This was always if
If
positive.
positive.
Yeah, if positive.
Good call, good call. We would have just gone forever. When I did this earlier, I used factorial instead of Fibonacci, so. Case number in, okay. That should be. I feel like I missed a close paren somewhere.
Well, yeah, you also just flipped
then an else, because it was if zero, now it's if positive, so.
Wait.
So this should be good. Now it no longer fits on one screen.
You're not closing your function call on line 148. You need another parenthesis. No, you don't need that comma.
Yeah. Okay. Can we still run our example one? Okay, great. Can we run Fibonacci in the default environment? Is 8 the fourth Fibonacci number? I have no idea. It seems right.
1, 2, 3, 5, 8.
8 is a Fibonacci number.
It is a Fibonacci number.
So, close enough.
That was very awesome.
All right, that's, and you can add every language feature to a language that you're writing an interpreter from, in whatever language you're writing it in. Sometimes it makes it easier, sometimes it's harder. Yeah.
Am I correct in assuming that you wrote this example for this talk, or did you write it for me?
I did, but it's so similar to countless examples that have been written before, that.
Well, okay, yeah, sure, that's fine.
Yes.
The follow-on question to that is, it would be cool if next month or something you show how to do a parser for puzzle.
Okay.
Okay, that might be really interesting.
Parsers are fun, yeah. I don't actually know the best way to write a parser in Swift, but that would be interesting to find
Use
out.
Swift parser library from the point free guys.
Or
These are on a lot of these.
github.com/Dave DeLong/ddmathparser.
Okay.
But
Only if you want a crappy
does
math
DD math
parser.
parser have support for functions?
It will, it's support for function calls, but not closures.
And one of the interesting choices you can make in defining this language is between this construct and this construct. The parsing between them is vastly different. But in the more general presentation that you usually see in interpreter contexts, function can be an expression, arguments can be an expression.
Part of the reason I asked that question is just because I think it would be interesting,
Okay, yeah,
especially
if there's
people
interest.
here who haven't seen this kind of thing, but also, frankly, in my own work, which is different than yours, I've never had to write an interpreter. I have written parsers lots and lots and lots of times.
I'm willing to bet that you have written an interpreter.
Sure.
You just didn't call it.
Yeah, I didn't call it that.
What was the
As
website
far
you
as
found?
parsers
So you've written a
go, this
compiler?
book is really-
Sounds
copy,
familiar.
Rob.
Oh, cool.
It's free online as well.
Yeah.
It's
It's a
fantastic
book.
book.
He types it
Mhm.
himself and everything. It's beautiful. What's
Yeah, the entire book is free online as well.
And there's so much you can add to it.
It's called Crafting Interpreters.
Crafting.
That,
Oh.
but the actual basics are remarkably
Is it as good
simple.
as the Dragon book?
Way better.
It's better in a lot of ways. Because it tries to also do things that are fully applicable to like everyday, like
That's
how
what-
you
that's
can
what I
apply it
was
to stuff.
Getting at.
And make a good parser because that's
I
what
think,
most of us do at some point.
I
And
think
Dragon
I'm-
Book doesn't care about parsing.
yeah, I think I'm halfway good at writing parsers. So I brought it up because it's a thing that comes up.
And
more
parsers
often.
are great. They can be separated from both interpreters and compilers, and I feel like they should be more often than they are. Because each is useful on its own. Like, you can use, that's a terrible way to do arithmetic. But if you have like Swift UI is sort of an interpreter with complicated view builder magic in it. But it's
Or
sort of-
even if you think about the syntax highlighting and, Xcode lets you edit your code, it's doing that by parsing Swift out into an
Yeah,
abstract syntax tree
yep.
and not compiling it.
Well, thank you.